So this is the part with the phase changes with the math examples. So this includes all the heat questions that you might see on the test and from your homework. Just as a prelude to this, we talked about graphing a phase change. So looking at the graph here, there's a couple different regions here in green, the solid, liquid, and the gas. That is where there is no phase change. Here in the blue, melting and freezing, evaporating and condensing, that's where the phase changes occur. We'll be using two different equations for each of these points on the graph. Phase changes, liquid to gas. There's this part about vapor pressure that's important. We didn't really talk too much about this, but basically, the higher the vapor pressure, so the more the particles evaporate, the harder it is for the rest of the water to evaporate. That doesn't come into effect on any of the math examples. So how do we calculate heat? Q is our heat value, and that's measured in joules. M is, of course, mass. C is that specific heat capacity that we've used all along. And delta T is the change in temperature in Celsius. So specific heat, remember, is unique for each substance. Here's the definition. And then the higher the heat capacity, the more energy required to change its temperature. So for example, water takes a long time for that to change temperature because it has such a high specific heat. Where iron, if you stick that into like a fire, for example, that will take a very short time for it to change temperature. So we start with these phase diagrams. So where temperatures are changing are in these three regions here. So where the temperatures are changing, we're going to use this equation, Q equals mc delta T. So an example question is how much energy is needed to increase the temperature 10.4 grams of cadmium from 64 to 325. The specific heat of cadmium is 0.231. So this is pretty simple. Take the grams, put those in the mass. Take the change in temperature, 325 minus 64. And then take the specific heat and put that in for C, and you're solving for Q. You know you're solving for Q because the question's asking for how much energy. So solving for Q. So, and the result of that is 630 joules here at the bottom. What does it say about when the temperature doesn't change? So when the temperature is not changing, the regions of this graph here and here at the plateaus, we use a different equation. That equation is this Q equals mH, where H is the latent heat of either fusion or vaporization. And so fusion correlates to if it's on the melting or freezing part of the graph, so down here, melting and freezing, or if it's at the vaporization, the boiling or condensing point. So going back here, now it's at this part. So this H value depends on where you are on the graph. The mass is the same, the heat Q is the same as before. This is important because this equation is used when there's no temperature change, but when there's a state change. So for example, how much energy is needed to melt 4 grams of lead? That's melting point. So the 10.4 grams, of course, goes in for the M value. The latent heat value goes in for H. And solving for that, you get 233. Another example. What was the mass of a sample of lead at its melting point that was heated with 73,000 joules with a latent heat of 22.4? So latent heat goes in here. We are solving for mass because what was the mass? And in here, the Q value is the number of joules. So again, solving for that, you get about 3,300 joules, or 3,300 grams, excuse me. Next question, how much energy does it take to boil 250 mils of water? 250 mils equals 250 grams. So that value goes in for the mass. We're looking for how much energy, so this is our question mark. And H, remember, latent heat of vaporization is 2260, so this value goes in here. Solving for that, you get 570,000 if you round it a little bit. So now, how much energy does it take to boil 5 grams of water that is at room temperature 25 Celsius? So this is a two-step question because you're starting down here and you first have to climb up the slope, then you have to climb across the slope. So how much energy? So we're going to be looking for a Q value. And so on this part of the graph we have Q equals mc delta T. On this part we have Q equals mh V for vaporization. Our total Q, the Q that we're looking for here, is going to be equal to Q1 plus Q2. So from the question we can find the mass, we find the C value that comes from your worksheet with the constants on it, 4.18. Change in temperature, we're going from 25 here to 100 here. So that's roughly 75 degrees Celsius. And so when we start to map this out, we have this Q and this Q together. We start plugging in values for these things. Our Q equals mc delta T value comes out to be this, 1567. So that's here. Our second Q value comes out to be 11,300, which is here. And you take and add those two together to get the total value. So about 12,867 joules. Here's another example. How much energy does it take to bring 250 mils of water from 40 C to 105 C? Latent heat of vaporization is 2260. So now, if we talk about phase changes, we're going to start down here at 40 degrees Celsius. That's going to climb up to 100 Celsius. Then we're going to change from a liquid to a gas. Still at 100 degrees Celsius. That gas will then change temperature to 105 Celsius. So I have Q1, Q2, and Q3. 3 parts of this equation. Same thing, we're going to have the different breakdowns of equations. So I just drew this graph before. We're going to start here. We're going to climb up to here, climb across to here, and then climb up to 105 Celsius, starting at what is 40 Celsius. So we're going to have to use both equations here and here. And we're actually going to have to use this one 2 times. So the first one, to heat it up to 105 or to 100 degrees Celsius, we set it up like so. We have our mass, our change in temperature, and our C value is of course 4.18. You end up with a value of 62,000 joules. The second part, where we are changing, this should be the H value here, H of vaporization. That goes in here. So we have our mass, we have our H value, we get 565,000 joules. That's Q2. Our Q3 value is from 100 to 105. So again, we're going to use Q mc delta T. Now the C value for steam is different than for water. Water was 4.18. We cannot use that anymore because it's in the form of steam. So the C value is a little bit different. Be the same thing for ice. But our mass doesn't change. The temperature is still 100 to 105. So you have 105 minus 100. When you solve with the mass as being 250, you get 2,500 joules for that small temperature increase. Lastly, you add it all up. So you have Q1 plus Q2 plus Q3. So here is 1, 2, and 3, and we solve to get 630,200 joules. Each question, it just takes some time for you to sort out what it is you're looking for. That concludes the examples I have for you. There's no quiz or anything you need to take following this video. This is just for study.